All right, good afternoon, everybody. I hope you enjoyed lunch. I'm here to talk about single-page application security. And before we start actually talking about security, I want to thank you for coming here. I know, since you're here, that you must be interested in security, in web security, and that's a great thing. I'm also fairly certain that here at the conference and at your company, at the water cooler, you're often talking about security issues, and one of your biggest enemies is probably the user. And I'm sure you think that users are stupid and users screw up and all your things are perfectly fine until the user starts working with them and then things break. So before I'm going to start my presentation, I'm going to give you a few examples to show why it's not always the user's fault and how nowadays we have many security problems where the user doesn't do anything wrong and still gets compromised or still becomes the victim. And that's essentially your responsibility. One example is of a password breach. This is one of Adobe. It's from a few years ago, but it's a really bad one in the sense that in this data breach, they didn't only get source code from Acrobat, or from Adobe products, but they also got hold of 150 million user accounts. That's user details, that's email addresses, passwords, things like that. 150 million, that's an astonishing amount. That's incredibly a lot of data. And it's out there on the web in public data dumps. The passwords were encrypted, by the way, which is not the best way to store them, but they also stored password hints, so people started building crossword puzzles based on the password hints and the actual passwords. So if you Google for Adobe crossword puzzle, you'll find a crossword puzzle based on passwords. Again, the user didn't do anything wrong. He just signed up for an account, and yet he became the victim of this data breach. If you buy a fridge at home, you can buy a smart fridge nowadays. Samsung has this smart refrigerator which runs, has a flat screen, it runs software, and it has applications to access your Gmail or your Google products, which is great. Except the developers made a mistake and they forgot to check SSL certificates, meaning that anybody could man in the middle of your fridge over a Wi-Fi network and start capturing your credentials to access your Google details. Again, the user didn't do anything wrong. The user merely bought a fridge at a store and wanted to see his calendar on the fridge. Again, it's a mistake. It's not a malicious intent, but it's a mistake by a developer that causes a security problem where the user becomes the victim. The networks all around us also have many security problems. We see these reports from malware being installed on routers, on home Wi-Fi devices, things like that, and it happens a lot. And these devices have very bad security on their interfaces. And they're vulnerable for all kinds of attacks. And what's even worse is we're getting accustomed to using public Wi-Fi networks we find everywhere. You're using the Devoxx network, but you have no clue, no idea what hardware is running the network, how secure is it, has it been compromised, is it running malware, is it intercepting your connections? You have no idea. And this actually happens, and this will happen more often in the future. And then on the websites themselves, you have advertisements, unless you block them, of course. But if you have advertisements, chances are something bad will happen every now and then. eBay and the Drudge Report had this problem. They had malware on there. It was available for 3 weeks. And that's a lot of users that have seen these bad advertisements. And even if the website doesn't host advertisements which get compromised, you have the superfish problem, which is the really big fish on the right. And that's an issue that was caused by Lenovo, who installed software on its computers. When people bought a new computer, you get all these kinds of very useful software on there. And this one was targeted advertising, and it actually man-in-the-middled all HTTPS connections by default, meaning that every Lenovo user became vulnerable to a man-in-the-middle attack on their HTTPS connections. That's the most secure thing you do on the web. Still, it's vulnerable. And again, the user didn't do anything wrong. So my message here is that users are more vulnerable than ever, even when they don't do anything wrong. Of course, users still do make mistakes. Users still choose the word password as their password and things like that. But a lot of things go wrong where the user doesn't do anything wrong and can't influence it either. And that's essentially your job. And that's why I wanted to start with this, to get your attention about why security is important and to teach you about single-page application security, which we'll do in a minute. So essentially, you should go the extra mile for security. And it used to be difficult. It used to be a mess, a web application. It was HTML, it was JavaScript. Everything was mixed together. You had server-side code composition, you had client-side code composition, and essentially it was a mess. There are also attacks like SSL stripping, where you really couldn't do anything as a developer to protect you from these attacks. So nowadays, the landscape has definitely changed. We have state-of-the-art technologies. We have a lot of new security policies which have become available and which actually give you the power to offer good security towards your users and to protect yourself against these attacks. And that's what we're going to talk about today. First, my name is Philippe De Ryck. I'm a postdoc at the iMine's DistriNet research group from KU Leuven. And I did my PhD on client-side web security, which is why I know a lot about these things. Since I finished my PhD in December, I'm building a web security training program under the wings of the university for now, where we essentially target practitioners like yourself and want to teach them how to build secure applications. And the reason we want to do that is because we do a lot of security research. We're sitting right on the edge when these new technologies are being developed, and when we talk to our industry partners, a lot of times we get questions like, how do we need to do this, or what's the best security option here? And that's why I decided that I wanted to go into training to essentially teach people how to build better web applications. During my PhD, I wrote a book on web security, which covers the entire landscape. It's a primer on client-side web security. It's available online if you're interested. And there we essentially look at the different attacker models on the web, the different attacks. We cover 13 different web attacks and their countermeasures. So I both look into the existing systems, what do they do currently, what did they do before, and what new technologies are available that should be implemented in the coming months or years. And that's, again, part of this will be covered here today. Before we talk about single-page applications, let's talk about traditional web applications. Let's talk about how things used to be back in the day. Let's say you have a simple to-do application. I'm not sure I have a laser pointer, but the screen is larger than I'm used to, so I don't think it's very useful. But we'll see. So let's say you have an application to create a new task. What used to happen is you fill out something in the browser, it gets sent to the server, where the server does a lot of processing. The server essentially starts parsing the request, stores some data, does a query on the database to build a list of tasks to return, generates some HTML, and sends it back in response. The browser gets this HTML and renders it. That's essentially a web application. That's how the web worked when Yahoo looked like this. That's about almost 20 years ago now. And the thing here is that the server does everything. The server knows what actions the user can do. The server pre-computes all possible actions. The server knows which input is coming in and which output is going out. And the server has all the context, all the information, and the browser is merely a rendering tool to display some information. Things used to be simple back in the day. Then they started changing. We had the need for to make applications a bit more snappy, to avoid the page loads and things like that. So essentially, we started working with APIs. Let's say you want to sort the list of tasks differently. Then in the Ajax days, you could send a request to sort the API, and you would get some partial HTML code in return, which you can simply inject in the page. This was a good evolution because you have partial updates, you have a better user experience, better performance, but it's still not a real application in the browser. It's actually it's kind of a hybrid form. It's something that is rendered and some updates, but the focus still lies on the server side. The server is still in control. The server still decides what is possible, and it's not a real application in the browser in the sense that you don't have offline support, things like that. And then come single-page applications, and they really shake up how web applications are being developed. And if you enter a task in the single-page application, it gets added to the list immediately. It's great performance-wise, great UI-wise, that's wonderful. Then in the background, this new item is sent to the server, where still the request is parsed, the data is stored, and a response is sent back. But the response is simply, fine, I got a task, it's stored, and everything is okay from my side. And this is a real application that's running in the browser, and this is essentially what is the big challenge that we're facing today. If you want to sort this application, you simply sort it on the client side. You have all the data, you have the processing power, the phone in your pocket is, I don't know how many times faster than the computer you had 10 years ago, so we can do this, and this is what actually happens. And here the focus lies on the client side. The application runs on the client side, the server is has become a data store with some APIs. But the challenge here is how do you correctly separate the client, the front end from the back end? And as I'll give a few examples later on in the presentation, this is where things can get really, really messy if you don't pay attention on how to do it correctly. So if you paint a small architecture picture, this is what this would look like in a single page application. So essentially you see that the server has a storage backend, but you also see that traditional components like session data on the left has moved to the client. You see that the client also has storage data storage. That's essentially the local storage or the index database you have in the browser nowadays. You have JavaScript APIs. You have, on the top left, the default browser security policies. They have been there since the first day that JavaScript was introduced, or maybe the first week or whatever. But they're still there, and they still govern how web applications work today. But we have added additional security policies both on the server and the client. This kind of architecture allows us to build applications like this. And this is a screenshot of Firefox OS. That's essentially an operating system for your phone that runs in the browser. So essentially what, under the hood, you load a microkernel. The kernel launches a browsing environment. And within that, the operating system is loaded. So if you make a phone call, it's a web application. This dial pad is a web application that will eventually call an API that's exposed by the kernel. And this is it's very cool. It's very evolved compared to what we had with Yahoo 20 years ago. But this also means that this is governed by web security policies. And this is why web security policies are so important. And this is why we see a lot of evolution in the recent years, because we need to enable applications like this. And if we don't enable them from a security point of view, then developers will find a way to do it anyway, with a less secure way. I'll give an example later. So in this architecture view, are two important things. It's the server sending policies to a client, security policies, and the client actually enforcing these policies. And a few examples of such policies, the simplest one is a cookie security flag. You all know the HTTP only and secure flag. If you don't, I suggest you really, really read up on web security because you're lagging behind 15 years. That's essentially the simplest version of such a policy. The server tells the browser this cookie should only be used on that connection. So the server is in control. And then we have started to see new policies appear. We have things like content security policy. I will talk about that today. That's essentially the newest security policy on the web and the most important one towards the future. You have cross-origin resource sharing. I'll cover that as well. HTTPS has got a drastic security improvement with two browser-based security policies, strict transport security and public key pinning. I will not be able to cover them today, but they're also really, really important and really interesting. So if you need to know about this, grab me after the talk and we can have a chat about that. What's also important is that these things make web security even more complex. And we already have configuration failures. For example, Google, they did this April Fool's joke where they put everything in reverse on their page, which is kind of funny. But doing so, they actually forgot to turn on one of the security features that's normally turned on Google. So they, with running their prank, they allowed malicious guys to frame Google pages and start executing click-checking attacks on that. That's definitely not the intent of the joke, but this happened. It's earlier this year. Another example, Match.com, they apparently had some configuration issue and they ran their login page over HTTP for a while until somebody discovered this and notified them and told them, like, maybe you should fix this, and they essentially did. But this is a configuration error. This wouldn't have happened if they would have enabled strict transport security, for example. And this is to show you that web security is complex, and we have a lot of vulnerabilities. These are two examples. It's the SANS top 25 of most common errors and the OWASP top 10, which you probably all heard about. And these vulnerabilities are present in modern web applications. These vulnerabilities happen a lot. And you should be protecting yourself against them. And if you don't take explicit action to protect yourself, then chances are that you're not protected, as I will show during the presentation. So I already hinted at what we're going to cover today. I have 4 major topics to cover. I want to talk about session management, especially in where you move to client-side session management. I want to talk about cross-site scripting, which is the single most important security problem in web applications. And I want to talk about 2 security policies, content security policy to prevent cross-site scripting attacks and cross-origin resource sharing to expose your API to third parties. So let's just start. Session management, I'll talk about cookies, tokens, server-side and client-side session management in a nutshell. But let's start at the beginning. Let's start with HTTP and state management. As you probably all know, HTTP is stateless by nature, so there's no way to relate two different requests together unless you store some states. You have no way to store temporary state, no way to keep track of properties about a user, things like that. So essentially, HTTP does support the sending of authentication data. You have the authorization header to send credentials. It manifests itself in the browser like this pop-up where you have no control over, that asks the user for a password, and it sends that on every request. This is very old. It exists for 30 years, something like that. It contains plain text credentials. If you use the basic version, you cannot log out using this mechanism. You can only close the browser, which is not very user-friendly. And essentially, it's not used today very often anymore. It's used mostly behind the scenes by some protocols. For example, if you have a Windows machine which uses a proxy, they use a form of the authorization header to send your credentials to the proxy. So how do we do it today? Of course, we use cookies. You all know cookies. A quick recap of cookie-based session management. You have a client on the left and you have a server on the right. And if you go visit the page of the web shop, the server creates a session and stores some data and sends you back your response, which contains a cookie as well. Setting a cookie is simple as that. You add a header, you add the name, the value, and some data about the cookie itself. Don't forget the secure and HTTP only flags at the end. They should be there if you're doing this. Whenever you send the next request, for example, to authenticate, the browser automatically attaches the cookie, which is great. The server recognizes the cookie, looks up the session, sees you're not logged in. Okay, you want to log in as Philippe, let me check your credentials. And if they succeed, we will store the authentication state in the session object. Sending a cookie is as simple as the one below. You send a cookie header and you send a name and a value. You may already notice that the set cookie header contains a lot more than the cookie header itself, and that causes various problems on the web, which I'm not going into detail today. So we have this session state at the server, great, we send a response, and the browser keeps attaching the cookie to any future requests, allowing us to look up which user we're talking about. That's cookie-based session management in a very short nutshell. If you have a second user, the same thing happens. Server creates a second session, sends a cookie is received, session state updated, and things like that. One comment here, you shouldn't use 1, 2, 3, or 4 as a session identifier. You should use long and random values as the framework chooses for you, which is definitely great. This is how session management has been done for the past 15 years, something like that. And this is how essentially every web application does it. If they use server-side state and they use cookies, this is how they do it. And this doesn't really work well with single-page applications and REST APIs, because REST APIs should be stateless, right? You don't see any state information on the server side. We don't care about that. So how do we do it in REST applications? We store the state on the client side. This has some advantages versus server-side storage. So for example, in a server-side session, you have a stateful API, which is a disadvantage, but you have full control over the session. If you want to invalidate a session, you simply destroy the object and the session is forgotten. If you want to track active sessions, you simply loop over the list of session objects and again you have the data. Client-side sessions don't have these advantages. They push all the state to the client, so the server doesn't know about a session until he gets a request containing some state information. This means that the server has no control over these sessions, and also that session data is transmitted with every request. This is how a modern web application most likely manages its sessions. We also have tokens, but I'm going to talk about them a bit later. So let me retake the example from before. If we have client-side sessions, we send a request to the server creates a session object, like before. The server then stores some data in it, sends a response, and attaches the entire session object as a cookie, which is sent to the client. So now the client has a session object instead of the server. Here, the browser attaches this cookie to the next request, of course. Server can extract the session data, see that the user is not logged in. Great, let's check the credentials, store some information, and send it back. Again, it's sent back in a cookie, and the state on the client is updated. Session Management 101. Next request happens, same thing happens again, and the response is sent back. If you have a second user, this essentially works like before. So you create a new session object, the blue one, you send it back to the client. The user authenticates, update the state, and send the state back to the client. This is really straightforward, but this is to show you that even with such a small change, things can go wrong really quickly. You may have noticed, if you have a bit of a security mindset, you may have noticed that the session contains an admin flag, which is set to false. In this example, if the blue user simply sets it on true on the client and sends it back to the server, chances are, if the server doesn't protect against this, he will just simply accept the state as being valid and make the blue user an admin. And this is because the security assumptions we had about our application have changed, simply by moving session state from the server to the client. So if you have this code on the server side, this is a very, very basic example, you get the admin flag from the session object. This doesn't have to change if you move the session data. If you have some middleware that takes care of this, you can access the session data in exactly the same way as before. The only problem is that now you may have a security problem in your web application. For those that have a bit of experience with security, if this seems like really, really trivial, you're right, but this still happens today in applications, so you're warned. And if these things are simple, then the more complex things will definitely be a problem. So what changes here? The client-side session holds the actual data instead of an identifier, meaning that if you mess with the data, then you can start manipulating the state of the session, while before you needed to guess an ID of an existing session to be able to gain access to that. If you would implement this client-side session management, if you use a middleware, for instance, this is the session middleware for Express on Node.js, you see that they add two cookies. They add a session cookie containing some data, and they add a session.sig cookie containing a signature of this data. And this signature allows the server to verify whether the data he receives was signed by him and whether it's actually valid data. This looks like really secure data, the session, because you cannot read it, but it's simply base64 encoded. It's not encryption. You can simply decode it in the browser and see what's in the session object. So if you would modify this views value in the session object, re-encode it and send it back to the server, it should be refused because it's not a valid session object created by the server. This is, if you're using something like this is what you should do. This is what the middleware should take care of you, for you, so you don't have to do this yourself. So let's say we have our API, we have client-side session management using cookies. How do you support that in your single-page application? You'll never guess the answer, by the way. It's really, really trivial. You run it in a browser. Browsers are made to support cookies. Every browser does. The browser automatically stores them, automatically sends them, so you don't have to take care of that yourself. If you'll notice, if you're running an application not in a browser context, then you will know how much a pain in the ass it is to manage cookies. It's definitely not fun. This is the main reason that we still use cookies today, because it happens automatically. You don't have to do anything as a developer, it just happens. And this is also the main reason that we have something called cross-site request forgery. So now we'll start talking about security. What is cross-site request forgery? Cross-site request forgery is essentially taking advantage of the fact that the browser automatically attaches this cookie wherever you want it to have it. So I have an example again. We have the browser on the left, and we have the shop website on the right. You simply visit the shop and you log in as Philippe, and you get a session cookie in return. Here for CSRF, it doesn't. CSRF is, by the way, the short version of cross-site request forgery. It doesn't matter whether it's a client-side or a server-side session. As long as it's a cookie, you're vulnerable to this. So what happens? You want to see the list of orders. You give the server your session state or session cookie, and you get the list of orders in return. Everything looks fine. Let's say you also visit a blog site by whoever, and it has been hacked. So you probably have a security problem in that blog. You visit this, you want the latest blog post, and you get a page in return. Notice that one page is green and one page is blue. This is because they're from different origins, and they are separated in browser. They cannot interact with each other, they cannot inspect each other. They're totally isolated by the same origin policy. However, in the background, the blue page requests, for example, to load an image from the somshop.com. But the image, instead of pointing to a PNG file, it points to an API call to change an email address. For example, change email.php with the email address of the attacker in the parameter. And SomShop doesn't really think about this. He had no idea that this would happen, because who would call this from another domain? It doesn't make sense. But the problem here is that the browser happily attaches your cookie to this request because it thinks this is going to someshop.com. I have a cookie for that. Let me attach that to the request so the server definitely knows who is making the request. And the server is not aware that this is a CSRF attack. He simply processes the request and changes the email address to the value provided by the attacker. And this is a CSRF attack, and it exists because the server is confused about the intentions of the user. The red request was unintended. The user never intended to send that. But because of the way the browser works and the web works, it was sent and processed by the server. This is a well-known attack. This is essentially, we have known about this at least since 2004, 2005 somewhere. And it still exists today, and it still happens a lot online. And the problem is that you need to take explicit action to prevent this from happening. So some examples about CSRF. eBay had a CSRF vulnerability. It actually led to a really, really bad problem where hackers were able to hijack user accounts. And essentially, what they did is they did the trick I showed you before with changing the email address. They first changed some of the user's details. When the user is logged in, they can do this in the background. You never notice it. And then they used the reset password feature, which used some of these things that the attacker has modified before. So, for example, call me on a phone number. But the attacker just changed the phone number using CSRF to his own, and eBay would call the attacker to do reset the password on your account, which is not the goal of this feature. Another great example, or a very sad example of CSRF, are home routers. They have a web interface. They use cookies to manage your session when you authenticate. And their security is really, really, really bad because they think we're in a trusted environment. We don't need to care about attackers. It's the user himself. Unfortunately, an attacker can perform a CSRF attack from the browser on your router. First, he sends login credentials in a hidden post request, and then he starts sending requests to change the DNS servers, for example. And from that point on, all your traffic is redirected to a DNS server or via a DNS server that's controlled by the attacker. And they use this for example, in phishing attacks. So they first change the DNS servers, and then they trick you into visiting an important website, and essentially it turns out that it redirects to a website run by the attacker. This happens a lot. I'm fairly certain that many of you have a device vulnerable for CSRF sitting in your home network. So this is definitely not good. But we know how to protect against this, and that's a great thing. And it's essentially, once you know how to do it, it's very easy and very straightforward. The first defense are HTML tokens. This is, again, from back in the day, how we used to protect against CSRF. Essentially, you hide the token in the HTML page, and you check the token on submission of the form. How does this work? A quick schematic. You have the browser and you have the shop. You want to see the account details page with your session cookie. You get the page in return. And in the page embedded is the blue token you see in the left corner there. This blue token is, for example, a hidden form field, something like that. And when you submit the form, the token will be submitted as well, and the server is able to verify whether the token that he receives is the same as the token as he handed out. And by doing so, he is sure that this request came from within the green page somewhere.
Isn't it holding state?
Yes. This is holding, the question was whether this is holding state. Yes, this requires the server to hold state, because this is how they used to do it back in the day, but I'm going to a better way to do it in a moment. So when the attacker does this, the request still goes out, the cookie is still attached, but the server doesn't find the token in there because it's hidden away in the green page, and there's no way the blue page can get to it. And the server will require the token and will essentially say, no way, I'm not doing this. You hide this, for example, in the form, with a hidden input field. But as has been pointed out, this is not very compatible with single-page applications and REST APIs where you don't want to keep state on the server. So a second way has been introduced, and that's using the origin header. Essentially, the origin header is very similar to the referrer header. It's sent by the browser on state-changing requests, like a post, a put, a delete, things like that. And it essentially contains the origin of the context that is sending the request. So in our example, when you change your email address, the browser automatically attaches this header saying that you're coming from someshop.com. And the shop is happy. If the attacker does this, the browser will attach the header from the website where it's coming from. It's hackblog.com. The server will see this and say that it's not a good request and he will not process it. That's one way. There's a second way, and that's the use of transparent tokens. And transparent tokens actually compare cookie values against header values. And it works something like this. You send a request and you get a cookie, let's say a session cookie containing your session data, and you get a second cookie which contains a CSRF token, which is a long random token that nobody can guess. When you send the second request, the cookies are included automatically by the browser. So you have the session cookie again and a CSRF token cookie. And then your client-side application, your JavaScript application, copies the cookie value into a header value. It has access to the cookies through document.cookie. That's fine. It can set a header on the XHR object, so that's also fine. And it attaches that, and the server simply compares those two values. So the server compares the cookie value it receives to the CSRF token it receives and checks whether this is valid. This essentially allows you to detect when an attacker is sending this, because the attacker will not be able to set a cookie for that domain, because that's protected by the same origin policy. The attacker will be able to set a CSRF token, but that's the only thing. So you will notice that this is definitely a problem. So this is well suited in modern web applications where you have stateless APIs, where you have JavaScript frameworks running on the client side, and you find a lot of libraries that actually offer this in a very simple way to configure. I have an example for Express on Node.js. You have the CSRF middleware. You simply configure it and have it send a cookie to the browser, and that's it. This will check automatically on the routes you have protected whether the token is there upon submission and will stop the request if it's not. In your AngularJS application, it's even easier. You don't have to do anything. If you use XSRF token as name for the cookie, then Angular will copy this automatically into a header and send it back. So this is definitely wonderful. I also have an example for the Ember.js framework, and there you have to do it manually, but you can simply add it as an initializer to your application, and then you will do it on every non-cross-domain request. So essentially, this allows you to protect against cross-site request forgery, which is a good thing. And as you see, it doesn't require that much effort, but it requires a little bit of effort because you still have to send the cookie. In the Angular application case, if you have an Angular application, great. But if your server, your backend, doesn't send the token in the first place, then Angular will never return a token, and you will be vulnerable for CSRF. So I promised I would talk about tokens as well, because cookies are essentially only a means of transport. You need some session data, and you need to hold it somewhere. And a cookie is convenient, so it's often being used, but there are cases where you don't want to use a cookie, or you want to use something else. So essentially, you can use whatever you want, as long as it's compatible with the web. The reason you want to do this is, for example, if you want to avoid CSRF attacks altogether, that's a good motivation, but also because cookie management is really difficult outside of a browser. If you have a mobile application and you have to do your own cookie management, that's really, really painful, and you definitely don't want to do that. So we have token-based session management. This is becoming very popular. Data is stored in a token, which is essentially JSON data, base64 encoded most of the time, and you add it to a custom header, to the authorization header, as a query parameter, as a form field. You have all the freedom you want. The only disadvantage is that you need to explicitly handle the token yourself. But again, that is very straightforward. A quick schematic of how it works. We have the same example as before. We log in, and we receive this token from the server in the response, and it's somewhere in the page as a piece of JavaScript, for example, stored in a JavaScript variable, out of reach for any other context. When you make a new request, you attach the token to the request. You have to do it manually. It's not done automatically. And the server is able to verify your session state, and everything is still well. In case of an attacker trying to do a CSRF attack, he will make the request. The browser will not stop the request, of course. But since the token sits within the green context, it will never be added to the request, not by the attacker, not by the browser. So the server definitely knows that there's no token and will not process the request as he shouldn't. So the responsibility here is for the client-side application to actually attach them to outgoing requests. And the great thing is it's not vulnerable to CSRF because they are not automatically attached, and you avoid the entire attack vector. And a popular way to do this nowadays is with JWT or JWT tokens, and they're essentially, they have become a standardized way of encoding session data, or claims as they call it, between two parties. So let me quickly run through this, how this works. It looks like a blob of data, like this big long thing. It's base64 encoded, and it contains a few different sections. First, the green one is the header. The header specifies an algorithm used for a signature and the type of token, which is in this case a JWT token. The purple part is the payload. The payload contains a few standard claims, like the issuer, the expiration date, and you can also add custom claims to it, like the admin flag in our case, for example. And then the final part, the red part, is a signature of both the header and the payload, and uses a secret key for the signature, so the server can verify whether the token is actually valid. This spec is part of a JSON-based identity protocol suite because they have some additional things to do encryption, signatures, and key exchange. And the main reason it's in there is because it's used by OpenID Connect on top of OAuth 2. So this is definitely something that will be staying. That is, I think it's a good thing to use, and it's definitely an easy way to store data in your application. You need to explicitly handle the token. This may be difficult in traditional HTML applications where you have requests that are actually sent by the browser. If you click on a link, you don't do anything. The browser makes the requests all by himself. But in modern client-side frameworks, this is very easy because it's all XHR, and you have control over how the requests are sent. So essentially, this is a very quick example in AngularJS. You can write an interceptor that looks for a token coming in on requests, stores it within local storage, so you have persistence, and you attach it again to outgoing requests in the application. So essentially, it's simple as that. You can make this as complex or as complicated as you want, of course. By default, the objects are base64 encoded, meaning that they are not confidential. So a client can inspect what the data that's in the token. You can use it, for example, if you want to update your user interface based on the permissions of a user and you store them in the object, then you can use that to update or to modify the UI based on the permissions. And if you want to store sensitive data, you'll need to add encryption to that as well. Integrity is offered by default because of the signature, well, as long as you use an up-to-date version, and I'm coming to that. This is widely supported. We have libraries for almost every language on the website of JWT, which is JWT.io. You have libraries for many languages. They also show which language supports what. And it's actually very well suited to exchange identity information between microservices, for example. Services can simply pass on the token of the user amongst each other to have your identity information. The problem is JWT has gotten a bad reputation lately because they had some security issues, which I'm quickly going to address. There are mainly implementation problems. They had a few stupid mistakes that happened. It's not a systemic failure. It's merely a hiccup, and it was quickly patched. So if you use up-to-date versions, you're fine. If you're not, then you definitely want to quickly update your implementations so they solve these problems. They had two problems. One problem is they supported the non-algorithm, which actually didn't do any signing at all. And this was a problem because the data coming in is controlled by the attacker who sits at the server side. And the attacker could simply generate his own token, not sign it, and use none as the algorithm, and the server would decide, oh, it uses the non-algorithm, so I won't even verify whether it's a valid signature or not. Definitely a problem, and they fixed it by preventing the use of this non-algorithm as long as the server has a key configured in its configuration. Second problem is a bit more complicated, so I'm not going into detail here. Essentially, it allowed an attacker to abuse a confusion between HMACs and public key crypto. This is a lot of details on how cryptography works. Essentially, it also allowed an attacker to abuse public information to sign his own token. And this is also fixed by depending on the server-side configuration instead of the information you get from the client side. This is to show that even library developers that are really experienced in these things do make these mistakes, so definitely don't try to do this yourself. And depend on one of the provided solutions which are vetted by a lot of people and are quickly patched if a problem is found. So, to wrap up session management, it's a critical component. It's present in almost every web application. It's And they also have security problems, as illustrated by the OWASP top 10, because two of the things we talked about here are in there. It's the second one, which is essentially broken authentication and session management, and the eighth one, which is cross-site request forgery. There is a difference between client and server-side sessions, and you should definitely take this into account, because if your assumptions change, then you will run into problems. Best practices to do here, you should deploy your entire application over HTTPS. That's unfortunately not one of the things I can talk about today, but something I'm really advocating for. Push HTTPS to the limit, and if you're at 100% HTTPS for your application, enable strict transport security, so you're definitely sure of that. You should always check the integrity and the validity of your client-side session data before you use it. And if you are using cookies, configure the secure and HTTP-only flag, and make sure you have CSRF defenses in place. If you have any questions, I think it's the most practical thing to just come talk to me after the presentation. I'll be here at the conference the rest of the evening as well. So that was session management. Let's move on to cross-site scripting. So cross-site scripting is a problem, security problem in many web applications. Again, it's not a new problem, it's a really old problem. We know how to fix it, or we have learned how to fix it, yet it's still really difficult to fix. I will, however, show that single-page applications offer you all the tools you need to actually get rid of XSS for once and for all. So bear with me, it's going to be worth it. First, to get everyone up to speed, let's illustrate how cross-site scripting works. So essentially, you have a client, a browser, which is on the top left. You have an attacker on the bottom left, and you have the server sitting on the right. In a cross-site scripting attack, or in this case of a cross-site scripting attack, the attacker is interacting with the web application running on the server. This is a shop application, and he simply asks the server to add a review for a certain product. Everything looks fine. In the review, however, you have the review, like I really recommend product X, or Devoxx is really awesome, you should go there. But the attacker also embeds a piece of script tag, which contains a piece of JavaScript code. This is the cross-site scripting payload, and it's shown in red throughout the schematic. The server is not aware that there's script in there, he simply accepts this, and thanks the attacker for the review. Until the user shows up and he wants to see the reviews, and he simply asks the server for giving a list of reviews and show me them. And the server responds with this HTML page, which contains the reviews, including the one from the attacker, and they are rendered in the browser, and essentially this results in a pop-up saying the alert message. This is a stupid example of cross-site scripting. It shows an alert box, nothing really bad happened, but there are much more severe consequences of cross-site scripting. If you're being rickrolled, for example, that's definitely horrifying for the user. However, also non-users can become a victim. I have an example from Apache.org. They had a cross-site scripting problem, a very minor cross-site scripting problem in 2010, and it led to a big compromise, which they fully documented, which allows me to show you step by step what happened and what has gone wrong. So essentially, they had this bug tracking system. I think it was a Jira system, and it allowed you to report bugs. And the attacker reported the bug, sent a bug report, which contained a shortened URL containing a reflected cross-site scripting attack. Essentially, he said, "This thing is broken. When I do this, can you please check it out?" An admin saw this bug report coming in, and as good as he was, he thought, "Okay, let's check it out. What's going wrong, and let's fix it." So he opens the link, and the payload of the cross-site scripting attack is being attacked in the session of the administrator. So the attacker essentially stole the cookie of the administrator. So now the attacker has the session data of the administrator. He's able to make a request to the application as the administrator, because the bug tracking software, he checks the session, it's a valid session, so he gives the attacker administrator access. There the attacker disables notifications for one of the projects on there, so he doesn't make noise when he starts messing with it. And he changes the location of file uploads to a path where he knows that it will be served, can be used to serve GSP files from. So the web server was configured to load GSP files from a certain path, and the attacker essentially changed the location for upload files to that path. allowing him to upload a GSP file, of course. So he adds a new bug report, which is why you want to disable notifications, by the way, and he adds some GSP attachments there, which are uploaded to the server. Then he navigates to the GSP page, which is loaded by the server, it's within reach, and he can do whatever he wants, essentially. He can install a shell script on there, using GSP, he can start copying files, going through the file system, installing, and he essentially also installed a backdoor, allowing him to gain access to the server again if he lost access because the session expired. So this is, now we have essentially an attacker having control over the server, all starting with a cross-site scripting bug. And this is only the first slide. I have a second slide continuing with this breach. So the attacker started messing with the application, and he installed a jar file to collect passwords when the user logs in. So he essentially modified the login form, so passwords are stored. Then he triggered a lot of password reset mails to trigger users to actually go to the application, reset the password, and log in. So he actually was able to capture passwords. He also started a brute force attack on some password files he stole earlier. And at this point, they're not clear how the next step happened, because it could be through either one of those mechanisms, but essentially, one of the passwords matched an SSH account on the machine with full sudo access. So at this point, the attacker has root access to the server running this bug tracking software. Definitely not good. Then he started going through the machine, and he found some user home folders, and he found some subversion credentials, and from that point, he could move on to the server holding the code repositories. He went to that machine, but he was unsuccessful to escalate to an admin account on that machine, because at that time they got onto the breach and they caught him. But would this have gone any further, in a day or whatever, no doubt, he would have found a way to access the actual code repositories hosted on there, and to start installing malware inside Apache.org software. And if you have looked at Apache.org, it's not only the Apache web server, they host a lot of code. And all of this happened because of a cross-site scripting vulnerability, a reflected cross-site scripting vulnerability, which is often discarded as not really being that important. So this is a warning. Cross-site scripting is really, really, really dangerous. So let's talk about what is cross-site scripting exactly. Essentially, cross-site scripting leads to the execution of attacker-controlled code in the context of the vulnerable application within the victim's browser. So essentially, in our example from Apache, the vulnerable application was the bug tracking software. Within its context on the victim's browser, the attacker was able to launch some code, and the victim, in this case, was an administrator. So the attacker was able to steal the cookie of an administrator, simply by injecting some code. The payload is provided by the attacker. It's malicious code. It can load additional files. Essentially, it can do anything a script can do in the browser. The victim's browser triggers the attack, so because it renders the code. And because of how the web is designed, there is no separation between code within the same context. So the attacker's code runs in the same context as the application code. There's no separation. The attacker has full access to the privileges that the application has. If you use location information, the attacker can access it. If you use local storage, if you store data somewhere, the attacker can access it. If you send XHR requests, the attacker can do it. And a lot of things can really, really go wrong. So you have three big types or three categories of cross-site scripting attacks. The first one is a stored cross-site scripting attack, and that's the example we already covered in the beginning. So essentially, it's stored because the attacker injects a payload, and it's stored at a server side somewhere in the database or some persistent storage, and the user, totally unrelated session, retrieves data containing the payload. The second one is reflected cross-site scripting, which was used in the Apache.org compromise, for example. And this one is even simpler than a stored one, and it works like this. You have again the client, the attacker, and the server. The attacker gives the victim a link some way or another. Here it's a mail. It can also be a bug report on the bug reporting software, for example. And this link contains a URL going to the application on the server side, and it contains some parameters which contain a script in this case. What happens is This link is opened on the user's machine. In this case, it wants to see a product, so it sends a request to the server, show me the product with identifier 1, and name the whole thing that contains the payload. Server does what is asked from him, renders the response. Here he uses the data from the request, which is a big mistake, as you will see in a moment, and sends it to the browser of the user, where this thing is rendered. It contains the payload, and it will, again, pop a cross-site scripting alert box. This is the reason they use an alert box is because it's very visible. It's a way to show a web application is vulnerable for cross-site scripting. You can collect your bug bounty if you found something. But in a real attack, of course, everything happens in the background and the user doesn't see a thing. This seems like stupid, who clicks on a link in a mail, things like that. Of course, this is just to show how it works. This often occurs in error pages. Search functionality, also vulnerable for that. And it can be abused in plenty of ways. For example, obfuscating a URL. You have no idea where it's going. You can load a hidden, if you already have a way to attack the user, you can load a hidden or a way into the user's browser. For example, I'm running a blog site, I contain a hidden iframe with a reflected cross-site scripting in the source, and I put it in my blog. Every user visiting my blog will be vulnerable for this attack. And this is why reflected cross-site scripting is such a big problem. And this is why you need to protect against this. Third one, DOM-based cross-site scripting is a bit more advanced. So you have the same parties here. We again send a link to the user, which is loaded. It contains some script code somewhere in the URL, which is not necessarily sent to the server. So we get a page, we get the page back, no payload, everything is fine. We render the page, and in the page is some JavaScript, and the JavaScript reads something from the fragment identifier of the URL, the thing behind the hash, and that is not sent to the server, so it stays in the browser. It does something with it. It starts injecting the payload into its own page because it's not aware that it's script code. It thinks it's simply the identifier of the product or something. And again, we have cross-site scripting. The thing here is the payload here is never sent to the server. It's never contained in the server response. The server has no idea that this happened. Yet, we still have cross-site scripting. So, enough about attacking with cross-site scripting. How can we defend against this? The best thing to do here is simply having secure coding practices. People used to protect against these things by filtering certain characters and removing the greater than or the smaller than sign. Essentially, this is not the right way to do it because you will not be able to catch all attacks. They use encoding, double encoding, a lot of weird shit that browsers do to avoid these filters. So not the way to go. What you should do is use context-sensitive output encoding. And in context-sensitive output encoding, you encode the dangerous or the untrusted content in such a way that it is relevant for the context you're running it in. And with an example, it will become more clear. You have all these different contexts on the client side. You have HTML tags, you have HTML attributes, you have style sheets, you have scripts, you have URLs. And in all these places, content is injected all the time, untrusted content. Most of the time, user-provided content, harmless content. But when an attacker comes by and he injects some data here, you will have a cross-site scripting attack. And it doesn't really help you if you remove the greater than or the smaller than signs in a style sheet context, because they don't mean anything there. There are other ways to execute a cross-site scripting attack from a style sheet. So this is why doing that doesn't really help anything. What you should do is use a library that actually offers context-sensitive output encoding. Examples are OWASP encoder, that's a Java library that does this. .NET has its own sanitization library, which is actually quite good. So this is how you should protect against XSS. This is how traditional web applications should protect against cross-site scripting. I'm coming to single-page applications in a moment. But even with this, we have cross-site scripting vulnerabilities all over the place. It's name a website and there is a cross-site scripting vulnerability for it, without a doubt. There's this website that keeps track of all of these vulnerabilities because you can earn money with that, so a lot of people are looking for that. Essentially every site from the Alexa top whatever is in here. Everyone, Google, Facebook, Twitter, eBay, Amazon, they all have them. And it seems really, really hard to prevent these, and it is actually very hard because you need to miss one spot. You need to misencode one output and you have a vulnerability. And if you think about an application from Amazon, for example, you can imagine how many outputs they have and how difficult it is to catch them all. So the question here is, can these JavaScript MVC frameworks help? If we have, in this example, if we have an API that returns some JSON code, isn't there a way that we can prevent this from resulting in a cross-site scripting attack? And I'm starting with the hybrid version of a single-page application. This is essentially not a single-page application, but I'm talking here about server-side template composition. I'm getting there. So here, we're talking about a traditional web application, for example, a Java application with GSP pages, and they use Angular to improve their user environment or to offer some routing features or whatever. So essentially what happens here is you start embedding an MVC framework which changes the way the DOM works in your traditional application. And this means that you can have tags that didn't exist before because you have created Angular directives that support them. You have all these kinds of extensions, you have new interfaces, you combine it with some templating in the page, and everything is wonderful. You have your traditional Java application, but you still have the power of an MVC framework. Great. What could go wrong, you might wonder? Well, scenarios where this happens is when you want to improve your UI with such a framework. And the problem is here that the server applies context-aware cross-site scripting protection, which is good. You know about cross-site scripting, you protect against it, and let's see if you're doing it right. This is a knockout.js example. You may want to guess that this results in cross-site scripting because it's in the slides. It does. Well, what's important here is the way you get there. And the way you get there is you have a div element with a data bind attribute. This, by definition, contains data. You have a script block with knockout script, which is essentially, it looks harmless. And if the server looks at this, it is harmless. The server sees it's a div with some data. Server has no clue that x:alert1 will be executed as script. How should the server of all people know, of all systems know, that this will result in JavaScript execution? And this is essentially a problem we have here. And this is the subject of this project called Mustache Security by Mario Heiderich. And this is a security researcher from Germany, which focuses on every possible cross-site scripting attack you can imagine. And he essentially looked at it in exactly the way I'm talking about it here. Let's say you have an injection vector on the server, which you have anyway. Let's say the server does cross-site scripting filtering, conventional cross-site scripting filtering, the right output encoding, everything you want. So essentially, let's say the server is secure against cross-site scripting in a traditional sense. What happens if you use such a JavaScript framework? Do you violate your own security assumptions? And we actually do, because we have a lot of bypasses for currently used security mechanisms, and I'm going to show you why it's a really bad idea to mix these things together. One example, Kendo UI, for example, you have a div block, and the div block contains some text content. It starts with a hash sign, alert1, and again a hash sign. And if you render this, this will result in cross-site scripting. Again, how on earth should the server know that what he puts inside a div, and he considers to be static data, that it will result in dynamically executed JavaScript code? There's no way for the server to know. Absolutely not. And that's part of the problem. Angular had a similar problem. I say had because it's versions before 1.2. You would include a div, make it an ng app, and you can do some fancy constructor thingies, which again, static data for the server. You push it to the client, and you get this cross-site scripting vulnerability. The Angular team actually took the research that this Myra guy did very seriously, and they fixed these problems. So essentially, they prevented you from breaking out of the secure sandbox in versions 1.2 and higher, so you will never have access to the alert function anymore, or you're not supposed to have access to it anymore. And this is why, if you remember in the beginning, I was talking about separating the front end and the back end from each other. And this is why you should really, really separate them and don't try to mix them together. You have dynamic behavior enabled by a JavaScript framework, which you have no idea of on the server, which you essentially there's no way you can protect against this. So you should keep these things really separated. If you separate them, the server gets, the responsibilities are reduced. You have an API and you provide data. And the client-side application contains a dynamic behavior. It's an application, it processes data, and it gets the responsibility to deal with it. This means that the client will have to deal with it. And that's what we're going to look at next. We're going to look at the real single-page applications, where the server simply sends data and processes data. The server has no context information, and the client will have to do everything to take care of cross-site scripting. So how does this work in AngularJS? I'm going to talk about Angular first. I also have an Ember example, which I'll cover in a bit after the Angular example. And I want to have an example case. Let's say a very stupid example. We want to have the user give some input, and we want to allow the use of the image tag because the user wants to include an image of a very cool car. So let's say we have this input element which results in stored in X, and we re-render this in the div. Simple data binding looks very easy, is very easy, and should work, right? We input our image tag for a really cool car, and we render this, and it results in exactly this, the image tag for a very cool car. So what happens here is we're not getting what we want. We want to see the car, and we're not getting that. And what happens here is Angular simply takes the X, the value of the X, and renders it in a safe way as escaped HTML. So this will be the lesser than tag and the greater than tag and whatever. Good if you have an injection vulnerability, bad if you want to see the car. So let's try ngbind. Maybe that gives something different. We try the same input again, and we get the same output again. Okay, that's not good. ngbind HTML, that exists as well. The name itself indicates that it will give us HTML, so we're really hopeful this time. We give the same input, and we get this error from Angular. And at this moment, you're getting a bit frustrated. You want to see the car. You're working on this for an hour or something like that. So you check the documentation. No, you go to Stack Overflow. And on Stack Overflow, you start looking for, I want to see HTML tags in my Angular code, and how does it work, and what can I do? And you find an answer from this Katie woman. And she says, yeah, you have to sanitize it to get it past the filter. And you can do it like this. Great. Copy, paste. Copy, paste. We sanitize the data. We input the data, our image tag, and we have our cool car. Great. Good job. We're done. So, what can happen? What if somebody inputs this? At this moment, you're hoping that Stack Overflow was right. You're hoping that please be protected, be protected. And you see the car, and you see this pop-up box. And at this moment, you may start to panic because you have introduced a cross-site scripting vulnerability in your application. If anybody needs to leave, you're excused. If you want to fix this, that's fine. So the question is, how did this actually happen? And if you would have read the documentation, which in my opinion maybe could be a bit clearer, but if you start reading through this, it essentially describes the problem we were having, and that's that we want to use an unsafe value in a safe context. And we want to, well, it doesn't make sense to do that, and that's what Angular also says, like you're not allowed to do this because it is potentially unsafe. And this is Angular trying to protect you from injection attacks, and Angular is actually really, really good at this. So you shouldn't work against it, you should allow it to protect you. Let me walk you through the different options. ngbind, as we saw, will never produce HTML. That's with the double mustache or ngbind itself. Never ever will it produce HTML. So if you use it like this, it will produce escaped data, which is good. That's the way it's supposed to work. So as long as you use this, you will not have a script injection vulnerability. That alone is wonderful. I mean, this is something that was not possible before these frameworks. And now we have it out of the box. ngbind HTML can produce raw HTML, but not without protection. So if you try to do this, you get this error. And this is to prevent the developer from shooting himself in the foot. Like, yeah, I want HTML here, just put it there. And Angular says, no, I will not allow this unless you declare this value as being safe. And there are two ways to do that. First way, you can sanitize the content. And this essentially means removing dangerous features. How would you go about that? We have the same input here above. We have the ngbind HTML, which is good. And we have ngsanitize. And ngsanitize, essentially, it's a module. It's available in the core. And it sanitizes the input. If you put this as input, it will return the image of the car, which is great. and it removes the potentially dangerous features, in this case an on-error attribute. And it does this for all the things you have in HTML. You have attributes of a form that are dangerous. You have on-error, and basically essentially any event handlers are dangerous, and it filters them out. And this is maintained by the Angular team, and they really do security well, so you can trust the way that they take care of this. A second way is if you really, really want raw trusted HTML, that's essentially to use the trust as HTML feature. And there you can mark a string as trusted, which will disable any protection that Angular offers by default. And this is what the Stack Overflow post suggested to do. And I think she didn't realize what she was doing, and that's how these bugs happen. And essentially, if you want to do this, you should write it like this, like a name that you know that this is potentially dangerous. And you simply return a string with marked as trust as HTML, which essentially says, I trust that this HTML is secure. I wrote this myself as static code. This does not contain any user input. And in that case, I want you to render it, which is fine. So Angular, really good at protecting you. Ember.js. This content was first presented in AngularJS user group, and I did the same presentation for the Ember.js user group a bit later. So I went looking into Ember.js with a friend, and we started investigating how Ember took care of this. This is a very similar example. Let me walk through it. You have the double mustaches in Ember as well, which outputs some data. Let's see what it does. You have the image tag, and you get, again, the HTML representation of this image tag, not the image itself, which is good. Ember, by default, offers safe output. Great. Again, we start looking for a solution, of course. We again find a wonderful Stack Overflow post suggesting we need to use triple stashes instead of double stashes. Okay, let's see what that does. We use triple stashes, we use the image input, and we have our car. Great. Wonderful. Of course, you may have guessed that we are actually doing the same as we did before, allowing an attacker to inject scripts using triple stashes, because in some way we marked this as raw HTML output. Not good. In Ember, you have something similar as in Angular. You have an HTML safe function, which marks a string as safe, and essentially that also results in a cross-site scripting vulnerability. The problem is that Ember does not offer sanitization by default. It's an all or nothing approach. You either have HTML or you don't have HTML. And there's no in between, like the ng-sanitize with Angular, that doesn't exist in Ember. So you'll have to use an external library. Before the Angular guys start laughing at the Ember guys, after the break, I have the example in reverse with some other technology, and there Ember beats Angular. So don't start laughing yet, because you can start a fight, and we don't want that here. So how do you do it with an external library? You have DOM Purify is a good example. It's written by Mario Heidrich, the guy behind Mustache Security. If somebody knows cross-site scripting, it's that guy. And essentially, you can integrate this in your Ember.js framework very easily, and you can push your untrusted HTML through DOM Purify, and it will produce sanitized HTML. This is a purely client-side library. It's the main advantage here is it uses the rendering engine or the parser from the browser, meaning that you won't have mismatches between server-side parsing and client-side parsing. So it's good, it's really fast, and I strongly advise to use this if you need sanitization. So to wrap it up, on data binding, you should always use the default binding mechanism, which produces safe output. If you do this, you're safe, you don't have to worry about it, and the frameworks are really good. Of course, if you use something else besides Angular or Ember, please check whether it actually does some kind of output filtering, because maybe there are some more obscure frameworks that actually don't do this well, but I have no idea about that. And if you need a safe set of HTML tags in the output, you need sanitization. You can do this with ng-sanitize or with an external library. Do not try to do this yourself. You will not succeed in being in resulting or in getting secure HTML or safe HTML code. And if you need to use the trusted HTML features, only do it for static code. Do it for some template you read in from a file where you know that there's no script in it, but never ever do this for a file that may contain manipulated code or user-provided input. That's essentially cross-site scripting. The built-in defenses have been covered. We're going to have a small break now, and after the break, I'm going to talk about content security policy, which also prevents the harm of cross-site scripting, and about CORS, which allows you to share an API across origins. Let's say that we have a 15-minute break. Should definitely be no problem. So I'll see you back here on 5 to 3. All right, let's continue with the next two topics, which are actually two new security policies which have been introduced in the past few years, and which enable behavior that was previously not available on the web as we know it. Let's start with CSP. I'm going to talk about content security policy, which is the single most important security policy for the coming few years. A lot of new security features are being added to CSP because they really want to push it forward and make it a really good security tool. So, what is CSP? Ember developers probably already know CSP because it's the annoying thing that gives you these big browser warnings when you build an Ember application. And you probably start Googling what the hell these report-only events are, and you find a blog post or whatever about a config file that you can modify, and you add some stars here and there, or you disable it completely, and the thing goes away. And chances are that you haven't investigated what CSP is. And CSP is a fairly complex beast. So maybe you tried and you were like, yeah, whatever, security, I don't care. Let's just disable it and we're done with it. And the thing is, this is a shame because CSP is really powerful and it can be really annoying, but it's annoying for a reason. And I'm going to show you why, and I'm going to show you what you can do with it and why you definitely need to look into CSP. Essentially, the goal of CSP is to reduce the harm of content injection vulnerabilities, and it does so by telling the client where the resources should be loaded from. It also disables dangerous features by default on the client. It's intended as a second line of defense against cross-site scripting attacks. So you should still do all the things we talked about before, but just in case you have some kind of vulnerability on the client side, CSP will be able to limit the harm that the attacker can do, or even prevent the attack altogether. It's a policy consisting of a set of directives, and each directive controls a different kind of resource on the client. I'm going to talk about that in a moment. The policy is generally delivered as an HTTP header by the server, and it will be enforced by compatible browsers when they receive the response, and non-compatible browsers simply ignore the header. So before I'm going to bore you to death with directives and things like that, I'm going to show you examples of what it can do for you. We have some cross-site scripting attack vectors. The first one is an injected script tag. This script is embedded somewhere in the HTML page, and it will trigger a pop-up dialog in this case. This is something that needs to be prevented by CSP if it wants to be useful at least. So CSP will effectively prevent inline scripts from running in the page. So you cannot write any script code between script tags anymore, any code between script tags anymore. CSP will simply prevent it from being run. XSS attack stopped, great. If you have remote script files, you can also inject this in the page, and then your script will be loaded and you will be running your code in the page context. CSP will prevent this from happening. Why? Because CSP allows you to specify a list of scripts or a list of sources where you want to fetch your scripts from. And unless you put evil.com in there, the policy will not allow your application to fetch that script, or not allow the browser to fetch that script, and will not execute it. Again, cross-site scripting attack stopped. If you want to use eval in a really bad way, for example, like here, you can still hurt yourself really badly. Again, CSP does not allow eval from being run in this way or in any way you want. So all string-to-code functionality in JavaScript will be turned off by CSP by default. So CSP stops a lot of things. Great. We go into details a bit later on the disadvantages or the difficulty of implementing it. But it sounds like CSP is really great, and it actually is. As long as you follow a few simple guidelines, CSP can do a lot for you. What does a policy look like? For example, this is a very simple policy. You have the header content security policy, and you say the default source for every content is self, which means your origin. If you have an application that doesn't use external resources, that doesn't depend on inline scripts, inline styles, things like that, then this policy essentially locks everything down. If you have an injection vector, an attacker inserts a script tag, it loads a file from somewhere else, it will not be loaded. It executes script directly, it will not be executed. Great. This seems really, really good. Another example, if you want to allow script files from a CDN, in this case, you can say default SRC, that's anything that's not specified anywhere else, is still myself, and for scripts, I'm going to be more specific, and I'm going to say scripts can come from myself, my own host, and from this Cloudflare CDN. You can imagine a CSP policy can become quite large if you do it like this. But it allows you a lot to block a lot of content. It started as a research paper by the Mozilla team. I think it was 2012 or something. And the aim was to give the administrator back control over the appearance of the site and over and give him some confidence where data is sent to. So CSP also allows you to control where forms are submitted or where XHR objects can connect to. And the goal was to do this even in the presence of an attacker that controls content. So people have realized that cross-site scripting is here. Cross-site scripting is probably here to stay for at least a decade longer. So with CSP, we are able to prevent harm from being done even if we have a cross-site scripting attack vector somewhere. So by default, CSP, if you enable it, it will prevent resources from being loaded from non-whitelisted locations. It prevents the use of eval, and it prevents inline content from being executed. Another example here, you can also restrict styles or allow styles to be loaded from the CDN, and you can use paths and a very specific file, and this is useful if you, for instance, have shared hosting somewhere. You don't want to allow the entire origin to serve you files, but only a specific file. So CSP has been well received, especially by browser vendors and the major corporations pushing browser development, like Google, Firefox, those guys. And it has started evolving very quickly. So they started adding new features. They started the possibility to restrict the use of certain plugins. If you want to disable Flash, for example, you can do it. They allow you to sandbox certain content, which is a bit more powerful than the HTML5 sandbox. You can say where forms are submitted to. So this is very useful. If somebody injects a form to steal some data from the user, this will not be allowed by CSP. They also added UI security directives to counter some click-checking attacks. And CSP essentially deprecates the X-frame options header, which is meant to prevent click-checking. They also have added some additional features to overcome some of the implementation hurdles we will talk about in a moment. CSP is widely supported by browsers, and Chrome is really pushing, well, Google is pushing for it, and Chrome makes CSP mandatory for Chrome components. So if you write in a Chrome extension or a Chrome packaged application, you will have to specify a CSP policy, and they even put fairly strict restrictions on the packaged applications. So you will have to write a very specific CSP policy for your application. Sorry, you have two versions. The first version is supported by virtually every browser. Even Microsoft supports most of it nowadays. And this is definitely very good browser support, especially for something that's so new. So, we already talked about what CSP does by default. Let's talk about what else you can do with it. You can use the default SRC to specify the default source of all content. And unless you override this for a specific type of content, this is the directive that will be applied on images, on scripts, on whatever. And the more specific ones, you have essentially a set of types of content. You have images, styles, fonts, child objects, media, and objects. These are specific content types, and you can specify a more specific list of sources for that. If you don't, then the default one will be used. You have connect SRC and form action. These ones are used to specify the destination of certain requests. So submitting a form is fairly obvious. Connect SRC started out as only XHR. Now it also controls WebSockets and other communication mechanisms. And then you have the sandbox and the frame ancestors directive as well. So in that light, if we have the policy from before, if you load an image, images fall under the default SRC in this case, they will be able to be loaded from anywhere. If you have a script, it must come from either our own website, images must come from our own website as per the default SRC directive. Scripts can come from our own website or the CDN, and styles can only be the bootstrap file from the CDN or our own styles. So this allows you to lock it down quite a bit. How about these content restrictions that CSP puts on, for example, scripts and styles? As I said, inline scripts essentially between script tags, will not be allowed to be used in your application. Same for event handlers. They're not allowed to be used because they are potentially injected by an attacker. And that's the essence of cross-site scripting. The browser has no idea whether your application provided this code or an attacker injected this code into the application. And that's what CSP tries to prevent. And you can bypass this content restriction essentially by putting it in an external file. Here we include a script file from our own domain and we put the scripts in there. At this moment, we are fairly certain that this was not injected by the attacker. The only way for the attacker to do this was to inject a script tag, which he can in an injection vector, and to also upload a script file to our web server or to our origin. And if he's able to do that, then we probably have worse problems than a cross-site scripting attack. You may imagine that this can be quite difficult to deal with, especially if you have an application that uses event handlers all over the place and uses script tags here and there, that you definitely don't want to start using JavaScript to add an event listener and things like that. There are a few ways you can avoid that. Script SRC and style SRC allow the lifting of restrictions using unsafe inline and unsafe eval. So essentially, by adding unsafe inline to our script SRC, we essentially tell the browser it's fine to run unsafe inline scripts. I trust that it will be fine. Essentially, this is definitely not recommended because this renders your protection useless. There are situations where you have no choice, then you'll have to use it. But the recommendation is not to do this this way and find a way around it. And that's what they added in CSP level 2. They added support for nonces and hashes to essentially allow a limited set of inline scripts and style blocks. And you do it like this. You specify a nonce in your policy, and when you include a script block, you add the nonce as an attribute. These nonces are randomly generated when a user loads the page or the resource. So there's no way for the attacker to guess what a nonce will be for a specific user, so he will not be able to inject a script tag. Of course, you should make sure that you add these nonces in a controlled way and not just find all script blocks that you can find, because then you will also cover the attacker's script blocks. This is a new feature. It's CSP level 2. Support for these features are a bit limited at the moment because it's actually very actively being developed, but support should be improving very well, or should be improving soon. One caveat is if you use these nonces and you depend on it, and you have a client that doesn't support these nonces, but supports CSP level 1, then you're in trouble. So you will have, if you want to deploy CSP level 2, you need to take the specific user agent into account. But don't fear. Coming towards single-page applications where this will be a lot easier than what I'm describing here. So, a few more examples. If you want to avoid any external resources from being loaded, you can lock it down like this. If you want to allow only HTTPS content from being loaded, you can specify the default SRC to be HTTPS. And by adding the unsafe inline and unsafe eval here, you ensure that all the rest of the content keeps working like it was before. You only restrict all the resources to HTTPS only resources, which is maybe something very useful to do in your application. So let's talk about CSP and JavaScript MVC frameworks. As I said, there are a lot of restrictions put forward by CSP for which you get a lot of power in return, but these restrictions seem like quite tough for MVC frameworks. And if you load your Angular application with CSP enabled, this is what you get. You get a lot of violations of the policy because you have inline scripts everywhere, and this is just not the way to go. Because, why? A lot of these frameworks depend on string-to-code functionality. If you write some string somewhere, Angular makes it code and executes it, and that's fine. They use eval, some of them, which is disabled by CSP by default. However, since CSP is so important and Angular is backed by Google and the Ember guys are very sensible as well, these frameworks are catching up rather quickly. And you actually can enable CSP in these frameworks, and I'm going to show you how it works. I'm going to start with Ember, because Ember enables CSP by default. So this is where you can get back at the Angular guys for not having sanitization. If you build a new Angular application, CSP is enabled. It's enabled by this module, and you can configure it in your environment file. There you essentially have two variables. You can choose a name for the header, which should be content security policy. It used to be a development header, but now it's finalized into this. And you can specify the policy you want for your application. The default policy that comes with a standard Ember app is the following. As you can see, it's locked down quite hard. They set the default SRC to none, meaning nothing. And they override the specific content types to only load files from the host itself or the origin itself. You can see down here that they have a connect SRC and a report URI. I'm going to touch on that in a moment. Essentially, the report URI allows you to send a report, and the connect SRC allows this. The reason that you have run into this when you're building an Ember application, with the error I showed before, is probably because you wanted to load content from an API somewhere. And once you start doing that, you violate the connect SRC, which is limited to self. And that essentially triggers these CSP warnings. This is great. It's enabled by default, meaning that we're making developers aware of this. They have to face the consequences. So now it's my task to actually teach them what CSP means and why they shouldn't simply disable it. So that's for Ember, and for Angular, they don't enable it by default. They offer a special CSP mode. So you can make Angular compatible with CSP, and you do it by simply adding ng CSP when you define your application. That's essentially it. By doing so, the Angular code base, or the Angular code knows it has to be CSP compliant, and it will not use any of its features that are not CSP compliant. And the reason it changes is they have to approach some things differently, but essentially everything keeps working in your Angular app as before, which is good news. They only warn that there might be a slight performance overhead on the client, but I think nowadays that unless you are really, really heavily using Angular features, that this should not be a problem. If you have any other experiences, please let me know. I'm always interested in hearing about them and seeing what's actually going wrong there. So how does this work in AngularJS? A quick overview. You have all these ng attributes, which is essentially an attribute containing a string that needs to be code. But what happens here is they actually parse this and use the strings to look up JavaScript objects. So if you want to execute the alert function, what it would happen is they look up this view object, and on that they look up the alert function, and that they execute with the arguments you gave before. Technically, this is not inline code, and this is not eval. This does not allow an attacker to inject anything unless Angular allows it to be executed. And that's why Angular has this strong sandbox starting from version 1.2. Because of this Mustache security project, they prevent the use from alert here because they know that that can be used as an attack vector. And essentially what they do is they prevent you from breaking out to the window object. You cannot reach any window function, so they know what they're doing here will be secure one way or another. And you have other dynamic behavior as well. Sometimes, for example, you need to apply some styles from JavaScript. You might want to do this, get this element by ID and set some attribute, and you get this big CSP warning. And again here, the browser tells you what's going on. It says like this violates the content security policy. It shows that style SRC is only self. You either need to add the unsafe inline keyword or use hashes or nonces to put this in a script block that's allowed to execute. The solution here is to use DOM manipulation instead of simply putting in some string into an attribute and having it parsed. So what you should do is use the approved ways of manipulating the DOM in one of these ways. And the reason that CSP is so strict on this is because it used to be possible to do a lot of bad things with CSS, like running scripts and executing user-injected content and things like that. But nowadays, these things are being removed from browsers because browser vendors are seeing that this was a really, really stupid idea to do. And they are removing some of these features, but that's mainly the reason why CSP is so strict on CSS, because it used to be very dangerous. So, to wrap up this content security policy thing, essentially CSP gives you a lot of control over what happens in your application context. It requires you to follow some coding guidelines. If you're building a new application, which is a traditional application with HTML mixed with JavaScript, really adhere to these guidelines so you can easily enable CSP on your application. If you have an existing application, this can be really, really difficult to enable. So that's a different discussion. CSP is really powerful, and especially in combination with the JavaScript MVC framework, because they are compatible. AngularJS and Ember.js do it really well. So take advantage of this capability and start working on your CSP policy after you've done visiting Devoxx. CSP also offers a reporting mode, and this reporting mode is great to get started building a policy and to learn about potential violations. And this essentially are violation reports, and every time that the browser detects something that breaks the CSP policy, he will launch a warning in the console, as I showed you some screenshots before. But it also allows you to send this report to a reporting endpoint where these reports are collected. And this allows you to fine-tune your CSP policy. For example, let's say you disabled a certain feature that you depended on, and you will get reports saying that this is a violation, and you will be able to fix it. And it also allows you to get insights into actual attacks. If you run this CSP policy, and some user has malware on the system, and all of a sudden you get a report which shows that it comes from malware, then you are able to act upon it, and you may start investigating whether you are a target of this malware or this is just a random incident. You can enable this with a report URI directive, and it looks like this. You have in your policy a report URI. It points to a certain endpoint where the CSP report will be collected. A report contains a lot of information about what went wrong. So you have the URI of the document, you have a referrer header where it's coming from, you have the violated directive, you have the original policy. So collecting these, you have a lot of information to see what actually went wrong and why it went wrong. Handling these reports, there are two aggregators out there that actually do this for you, but I've tried them both a few months ago and they were really not very good. They simply collect the report in JSON and show you the JSON, but they don't really do anything with it. Of course, you are free to implement your own if you want to. The feature is here. Other policies are starting to incorporate a reporting feature as well, so this is definitely something that will be available in the coming years. You can also deploy CSP in report-only mode. And here, CSP will not block any content. It will not prevent an injected script from being executed. It will merely launch an exception and log this in a report if you have a report URI. And the good thing is here, this is, by the way, how Ember enables CSP by default. And the good thing is, as a developer, you will get these warnings during your development, during your testing. You'll see like, oh, I get a lot of warnings here. I'm probably doing something that's not allowed by CSP. It's great if you want to deploy a CSP policy on an existing application. If you make a mistake doing so, then you block a large part of resources from being loaded, and you may influence the operation of your application. So my advice, deploy it in report-only mode and see what happens. And if you don't get any warnings for a few weeks and people are still using your application like they did before, then your policy is probably fine and you can enable it in blocking mode. The report-only requires you to modify the name of the header. You should add report-only to the end of it, and then you specify the policy as before with the reporting URI. This is really powerful. Even if you don't want to deploy CSP for your application, you can still deploy the report-only mode to get insights into attacks, for example. I know of a bank that's doing this to stay up to date on what malware attacks they're seeing and what scripts are being injected into pages at the client side. This is something that you were not able to do before. You had no idea what happened with your page on the client side because you did not have control over that. Now the browser offers you control over what's happening with the page with CSP. That's great. So, essentially, using CSP in combination with traditional cross-site scripting defenses allows you to really, really lock down your application and to really prevent harmful cross-site scripting attacks. Even if there's an injection vector you overlooked, chances are your CSP policy will knock it down immediately and you will not have a problem. And it brings me to my final topic, which is cross-origin resource sharing, or CORS in short. And essentially, this is about sharing resources across origins, surprisingly enough. But it's one of the new security policies where they enabled behavior that wasn't possible before. And there are some interesting catches to that. And I'm going to explain why CORS, if you know it, you know what I'm talking about, why it's so complicated. So let's go back to the old days. Web applications did not rely on APIs. So you used to load HTML data and you get something in return. But of course, the web evolved and people really wanted to use at least some part of an API, but the browser really would get mad if you tried to do so. If you do a cross-domain or a cross-origin, cross-site XHR, in an old application, I actually had to download Firefox 3 to get a screenshot because all browsers allow it nowadays. If you would do this, an XHR, to another origin, the browser would simply give you this exception and say that it was not allowed. It was fun to see, by the way, that Firefox 3 still works perfectly on a Mac. You simply download it, you launch it, and there you go. Very great. So you would not be allowed to do this. So you could not fetch data with XHR from another origin. That's definitely, if you look at modern web applications, not something that you want. So you want to do this, really want to do this, but the browser doesn't allow you to. And then we started having Google, and we started having Facebook, and they had APIs. Facebook had this Graph API to give you your Facebook friends, and Google had Gmail, and you had a contact list, and people really wanted to incorporate this in their web application, but the browser wouldn't allow this, and vendors wouldn't want to support this, and things like that. So, as always, if you restrict a developer, he gets creative, and they found ways around this. They started using server-side proxies, and they started using JSONP to actually get the data behind the browser's back. Like, if you don't want to support this, fine, I'll do it my way. We'll see in a minute that these things are really, really, really bad, and you shouldn't do this nowadays, but they have sparked the invention or the development of CORS, so they had some good consequences. Server-side proxies, and why they're a bad idea. We have the client, and we have the server, and we have a third server which offers us some information. We load this page from our example.com server. It's loaded in browser, everything is fine. We want to load content from this websec.be with XHR. This is really not allowed in the browser, so we cannot get it directly. So we simply ask our server where we can connect to with XHR, like fetch me this content, please. Server obeys very nicely. This is a server-side proxy we're talking about, and he gets this content from websec.be and returns the content to the browser. Why is this a bad idea? You may have noticed that on the right, the response page is blue, and on the left it's green. And these colors indicate the origin. So on the right, we have content from websec.be, which is being sent to the browser under the origin example.com. This means that the content has switched origins, and the server doesn't care about this. The server isn't influenced by origins, but the browser has this thing called same origin policy, which separates content from different origins to avoid them from influencing each other. And here, you all put it together, you mesh it together. These are the so-called mashups we had a few years ago. You put it together and you get this big blob of data where some stuff comes from Google and some stuff comes from Facebook, and essentially you have no idea what's happening anymore and you have no control. This is not a good idea, but it happened because the browser was too restrictive. Same thing with JSONP. It's called JSON with padding or JSON with prefix, depending on where you look. How does this work? Again, you have the client, you have two servers. We load the page, and then instead of going through the server, we contact the website server directly with a script tag. We include an external script, which is something that has always been allowed in the browser. You only don't get access to the contents of the script. It's being parsed and executed, not shown in clear text. And what you do with the call is you attach a parameter, a callback parameter, with a name in there. It's the name of a function, because if you get this content, you get this response in return. And essentially here, you see that the name show users, which we passed to the server when we made the request, is now being used in the response to process the JSON data. And this show users function is meaningful inside our page. We have defined it ourselves. And this allows us to extract the JSON data from the script file that's being loaded. Essentially, this, after the talk about cross-site scripting, you should see that this is cross-site scripting by design. This essentially allows you, or gives trust to this third party, and if the third party decides to inject some scripts in your page, he has all the power to do so. He is totally free to inject whatever he wants in there. And this is, again, not a very good idea. This is not how you should do it, but this is what happened anyway, because they really wanted the data. So things became very, very messy. We had a quickly evolving landscape. We had major corporations like Google and Facebook pushing forward. And more people started offering an API, and we didn't have a way to integrate the API, so we needed a way to have API access by design regardless of the origin. So why don't we simply allow XHR to access APIs on our origin? And that's essentially what cross-origin resource sharing does. But the spec is 22 pages of specification, simply to allow that. So this may be a hint that it's not so easy as you might think, because there are some really serious security issues that will arise when you try to do so. So let's see why. What if we simply allowed XHR across origins? Again, we have our browser, we have our servers, we load this page, and we XHR the user's profile from websec.be. The JavaScript code to do this looks like this, very straightforward. XHR request, get the URL, and you get the response text in return. If you alert this, it looks like this. This looks fine, right? What could possibly be wrong with this? Well, essentially, the site, the context from example.com, the green context, has no business inspecting the HTML of a blue page coming from websec.be. This is something that was never possible on the web, and it shouldn't be possible, because this page, imagine that this page contains CSRF tokens. You can extract them, for example. Not good. Imagine that instead of websec.be, it's your bank application dot whatever. Now you can inspect the HTML from the banking page, including your credit card information, your account details, everything you want. Definitely not a good thing. Shouldn't do this. Same thing if you load a script file from a remote server, you get the actual script contents. Again, access to the source code of a script should not be allowed. It has never been possible on the web. You can use a script tag to execute scripts, but not to read the really raw content of the script, at least from the client side. Shouldn't be possible, but would become possible with XHR. And the same thing goes for headers, which you can inspect in your XHR object, and which you shouldn't be able to, because this contains things like cookies and tokens and all information that shouldn't be inspected. So to conclude, cross-origin XHR is really dangerous. And that's why CORS put some restrictions in place, and that's why the specification has become a bit complicated. So what does CORS do then? CORS allows the server, in our case a web server, to tell the browser that a resource can be accessed by a certain origin. Essentially, you can see CORS as an extension of the same origin policy, as kind of a relaxation, but controlled by the server of the application. The browser enforces these checks on each call, and if everything is okay, the response is granted access, otherwise access is denied. So let me show you how that works. We have the scenario from before, and the browser sends this origin header to the server, which can verify, do I want to give a page coming from example.com access to this resource? Well, maybe I do. In that case, let me send a header back to the browser saying that I allow access to the origin http www.example.com. The browser sees this and allows the client or the context to inspect the result of this response. So in this scenario, you get raw access to the HTML page, to the source code, but only because the server said it was okay to do so. Very, very important nuance, and that's what what CORS enables for XHR. We have credentials. I talked about cookies and tokens before. Again, we have them here. They belong to a domain, so should they be sent or not? How do we need to deal with them? Well, CORS specifies how to deal with them. CORS only applies to cookies, by the way. It doesn't take tokens into account. You'll have to deal with that manually. The server should acknowledge the use of credentials if you want to, and only then the browser allows you to access the resource. Otherwise, access is denied. So it's clear if I give you an example. We have the same scenario. If we make the request, we specify this with credentials flag to be there. You need to specify it, otherwise it doesn't include cookies, because by default cookies are not included. Okay, if we do so, the browser attaches two headers, the origin header, which is always there in the course request, and the cookie header, which is now allowed to be attached, so the browser does it for us. And we get this response from the server. First of all, we need to allow the origin to have access, so that's okay. And then we need to say to the browser, and by the way, I'm fully aware that this request was made with credentials, and I want to allow this actually from, I want to allow this, so you can give this script access to the contents of the response. The clue with CORS is all about protecting requests being sent from the browser, because any attacker can send any request he wants to any web server. So he doesn't have to go through a browser. He can send arbitrary requests. He can send malformed data, whatever. The clue here is you want to protect the use of the user's cookie, which only lives in the user's browser. So CORS prevents attackers from making requests in the user's name with credentials to an unknowing server. There is, however, a catch. If you would only have this, then we would have maybe 5-6 pages of spec, and we have 22. So there is a catch that we are missing, and the catch is here. We have legacy servers. If we send this request to websec.be, the browser attaches the origin header. But if websec.be doesn't really know about CORS, he has never heard of it. This thing is running since 1998 or something. If he wouldn't put a restriction on there, then things would go wrong. So if you do this and the header is missing, the browser simply says that this is not allowed because you are missing the access control allow origin header. And the reason getting information may be potentially dangerous, but there's more. If we send a request to delete a user's profile from websec.be, that's also valid on the web. You can send a delete request using the delete method. The browser includes the origin header. The server responds saying, without a header, saying this is not allowed, you shouldn't have access to the response. But at this point, it's kind of too late because you've made a delete request, the server has processed it, sends a response back saying, okay, profile deleted, see you. And then the browser says, oh, but you're not allowed to see the response. And that's the second complication, of course, and that's essentially the biggest one. And that's the one I'm going to go into detail on why this is here and how CORS solves this problem. So, sensitive data is protected by denying access. That's the standard mode of operation for CORS. That's for simple requests, and that's because these requests and responses were possible on the web before. But with modern APIs, a REST API, for example, he offers delete methods, he offers put methods. And they trigger state changes on the server. And if you only enforce a security policy after the response has been received, it's too late. So here, we need to do something up front. And we need to make sure that these requests are only sent if the server really wants to accept them. And that's why CORS is so complicated, because if you start enabling XHR to go across origins with a delete request, which was never possible before the launch of CORS, well, security assumptions change. A server may not expect a delete request from anywhere else except his own origin. So you need to take care of that. A few examples of things that were not possible. Access to the response of cross-origin gets, we already covered that. Cross-origin puts and deletes used to be impossible. They actually discovered this vulnerability in the HTML5 spec as well with form elements. Using in research, they did this whole theoretical model of browsers and web applications, and they specified HTML5 in there, and they discovered a violation of one of the implicit assumptions that this was not possible. So they have updated the spec to prevent this, and in XHR, they actually require explicit action to enable this. And cross-origin post requests were always possible, of course, with forms, but only with forms, not with custom data, not with file uploads, not with whatever. So again, this is something that we need to cover. And this is what CORS does. CORS makes sure that these assumptions of things that used to be possible in the old web before CORS are still possible, and additional functionality that wasn't possible is only possible if the server is CORS aware and agrees to the request. And this brings us to simple and non-simple requests. And that's essentially what the course spec spends a lot of time on. And that's essentially what you need to understand the power and the importance of course. So simple requests are all those requests that were already possible in the old web. It's what you could do with image tags, what you could do with script tags, what you could do with forms, and things like that. And for these requests, it suffices to protect the malicious code from accessing the data in the response. If you deny this in the browser, you have the same protection as you had before. For non-simple requests, they add new capabilities. You need to protect this before you execute it, and Course does this with a pre-flight request. So essentially, whenever Course detects a non-simple request from leaving the browser, it will stop it, and it will send a pre-flight first, which essentially checks with the server, are you okay if I send you this? Because this wasn't possible before, I'm going to do it now. Are you okay? And if you're not, I'm not going to do it. And that's essentially what happens in this flow of a pre-flight request. So again, I have a schematic, we load a page, and then we start doing some cross-origin XHR, and we want to delete the user's profile again. And what happens is the browser detects this from happening, detects that this is happening and stops it. And first he sends this options request, and this is a special request to ask more information. It has been in HTTP since the beginning, but it was never really actively used until now, of course. And what it does is it sends this request to the server saying, I want to access this URL. I'm coming from example.com, and I request if I can use the method delete. Please advise. And the server responds. He says like, okay, I allow example or www.example.com access. That's fine. And for you, I allow get, put, and delete for this URL. Okay, fine. So the browser is like, great, let's send the delete request. It again includes the origin header, and the server processes this and sends the access control allow origin header in return. And this is how you can enable delete methods without affecting existing servers, without adding new capabilities, unless the server actually agrees with doing so. And this is, believe me, if you read the specification, this is a lot of text to explain this concept, and there are a lot of corner cases that are covered as well. But this is the essence of the protection that Course offers against legacy servers. So how do you configure such a pre-flight, or how does it happen? It asks for permission based on the data that will be sent in the actual request. So if you send a pre-flight, the browser will include the origin header. It will include a request method header to say, what am I going to do? And you can also include a header, a request headers header to specify, by the way, I want to add these custom headers to my request. Are you okay with that? Then the response on the pre-flight contains the allow origin, as with all Course requests, and that needs to be true, or needs to match the origin that made the request. You can specify the methods that you want to allow. You can specify, okay, I'm okay with get, post, put, delete, whatever. You can specify which headers you want to allow in the request. So this prevents a malicious application from sending a request with a header that would confuse the server. If you use this custom header for authentication, for example, you definitely don't want to expose this to any XHR request, for example. You have a max age, which influences caching. So the max age request allows you to specify how long the pre-flight response is cached in the browser. And you can specify whether credentials are allowed or not. And then on the actual request, you have this allow origin. That's the response headers on the actual request. So this allow origin, we already covered that. Expose headers. This allows the server to tell the browser that the script can have access to certain headers that are sent on the response. Again, this allows you to protect sensitive headers from client-side JavaScript. Allow credentials to enable credentials, and that's essentially it. So by doing so, you can protect your API from being attacked with Course. You as a developer need to specify a policy. There is plenty of framework support or middleware support to do this for you. So you don't have to bother with the really dirty details. They also handle the options requests for you and things like that. Pre-flights are cached by the browser. That's very important. Why? Because they add some additional load, because you need an additional round trip for every non-simple request, and that can be become quite large. So this allows you to cache this response for quite some time, avoiding you to make the request again. And this is where we go back to session management. If you used cookies, you could use the with credentials property to simply send your cookies. If you're using JWT tokens and you need to send them on your XHR request, then you will have to add them manually. And this makes a request non-simple because it's a custom header, and it will require a pre-flight request. So this may be an interesting choice if you're choosing between cookies or JWT tokens. You may want to take CORS into account. In practice, CORS is supported by virtually any browser. There's only one missing, which is Opera Mini. I have no idea why, but CORS is widely supported. It's very well accepted, so definitely something worth thinking about or using. In practice, many frameworks support it, and many publicly available APIs already offer it, because we had the JSON thing to include context. Well, nowadays, Google, GitHub, Twitter, Amazon, they all offered their APIs with CORS headers, specifying that anyone can include it or certain parties can include it on how to do it. So if you want to join them, how do you do that? If you want to offer your APIs, even to a partner website or to everyone, you will have to configure your own CORS policy. Some guidelines to do that. If you have resources that should not be accessed by other origins, let's say sensitive resources, login pages, things like that, simply don't send any CORS headers, and nobody will have access to them anyway. That's the default deny behavior. If you have publicly accessible resources, non-sensitive resources, scripts that anyone can access, JSON APIs that anyone can access, you can use a star. And this star essentially is a one-time configuration in your config file, and you don't have to look at it. It doesn't have to be a specific origin. Essentially, it means anybody can access this. And that's what, for instance, a Google or a Twitter would do on its public APIs. It would simply add a star, and it wouldn't care about any configuration any further. Simply, same holds for JavaScript files that do not contain sensitive data or comments. You can simply allow them to be fetched, which enables certain client-side processing behavior that wasn't possible before. Then onto the more interesting things. If you have credentials on a request, things become a bit more complicated. It's not a simply public access anymore. It's something that's authenticated, that potentially will be processed within the context of the user, so you need to take additional stuff into account. What you should do first is verify if the value of the origin header matches one of the accepted origins, one of the origins you really want to allow access. If it's not, abort without sending any headers. Simply don't send anything back and send an error response or whatever, and you're fine. Next, you should verify whether the user is actually authorized to access the request service. This is your authorization as you should have done it before. Of course, here you need to take the method into account. Is it a put or delete request, and some custom headers that may be sent as well. If your check fails, if this is not allowed, abort without sending any headers. Send it back to the browser and say, I'm not going to do this. Fine. And then, if you really want to allow it, then you end up at the final step, and here you set the allow origin to the specific origin that you received in the origin header. You allow credentials if you, in this case, you want to allow it, so you set it to true, and you can expose certain headers. For example, you want to allow the client to access the X API version header you have set to version 6 or whatever. And that's essentially how you configure a CORS policy on a server. There's one final thing I want to cover, and that's CORS policies beyond XHR. CORS was invented to allow cross-origin XHR, and then they started seeing that a lot of other content is XHR as cross-origin as well, and a lot of other things may need additional protection from manipulation across origins. And they have extrapolated CORS or extended CORS to apply to several HTML5 elements as well. And essentially the same principle applies. We have some elements, for example, the canvas element allows you to draw images and videos. And if you don't protect images from other origins, then people would be able to extract information from the images, what was not possible before. Same thing for multimedia elements like videos or audio tracks. They have subtitles in HTML5, or they can have subtitles. Again, they can contain sensitive information that can be extracted if you don't have any additional protection. So an example of how this works with HTML5 canvas. If you have a browser on the left and a server on the right with an image, and we include this with an image tag. This is essentially what has been possible for 30 years on the web already. This image is loaded in the browser, it's rendered, and it's displayed. As a script, you have no access to what's inside the image. You can get a width and a height, and maybe the source and stuff like that, but you cannot have access to the actual pixel data of the image. You have no idea what the image looks like. With a canvas, what you do is you specify this onload function on an image, and you fetch the image. And then you can draw the image on the canvas, and a canvas offers ways to extract information from images. You can parse it to a data URL. You can get the very specific information on one pixel. And that's shown below. For instance, if you get this image data, you get this pixel array, and you can start manipulating it. You can change the color of the image, things like that. But you can also get information. If you go pixel by pixel, you can extract exactly what was in the picture. And that was not possible before, and this shouldn't be possible today. And that's essentially what the browser prevents. The browser will throw a security error if you do this. It will say that the canvas is tainted, and it may not be exported. And it means here, tainted means it contains content from another origin. I will render this for you. I will allow you to draw this video on your canvas and to apply some effects to it, but I will not allow you to extract the data because you were not able to do that before, and you will not be able to do it now, unless you use CORS. If you do the same thing, we make a cross-origin request from JavaScript to an image. You can either specify whether to use credentials or to do it anonymously. The browser will attach an origin header, and the server has to respond with an allow origin header in return. If you do this, then the browser knows the canvas contains an image where the server acknowledged that it would be used in that way, and that's fine. And then the canvas is not tainted, and you can export the data from the canvas. That's one example of how this works, and they're using the same thing with videos. And if you allow the content of the videos or the subtitles to be exposed to example.com, then it will be able to inspect the contents as well. And that essentially leads me to the wrap-up of what we talked about today. And we have covered CORS now, and we have 4 security topics. And the main lesson I want to teach you, or the main topic I want to bring across, is that single-page applications differ from traditional applications. We have client-side applications, we have server-side backends, data-driven backends, and you have a lot more responsibilities that we need to cover. And we have the tools to do so, but you need to be aware of how they work and what they do, what they imply, or what assumptions they change before you are able to effectively build a secure application. And as I have shown you, we have the tools to build really secure applications. We have, for the first time in the history of the web, the possibility to get rid of cross-site scripting by using the right tools and applying the right security policies. So allow me to give a quick recap of the topics that we covered. So for session management, we had 2 approaches. We had server-side sessions, where you have all the control, but you have state that needs to be kept on the server. For client-side sessions, you get flexibility, but you need to make sure that you have integrity or confidentiality if that's important to you. You can do this with cookies. They are widely supported in browsers. I had some questions during the break about cookies and tokens, and essentially it boils down to cookies are supported, but they lead to CSRF. Tokens require a bit of effort by the developer, but they fit much, much better in an API landscape. It's much easier to pass a JWT token between microservices than to start passing the value of a cookie, for example. JWT is built to that. JWT contains an issuer. If you identify, your users identify with google.com and you get a JWT token in return, then you can inspect it and you see it's issued by Google. It's signed by Google. It claims that the user is philippe@gmail.com, for example. And that's essentially the goal. And what's important here is you have to constantly evaluate your security assumptions. You have to think about, is this data coming from the client or from the server? Can I trust it? Can't I trust it? What changes if I put this on the client? Do I need to add additional protection or not? Second, cross-site scripting. You should really be scared by cross-site scripting. If you're not, come talk to me during the break, after my talk, and I'll tell you a few stories where you really should become scared of. The Apache thing was a good example. You had a cross-site scripting flaw, which led to the compromise of the source code repositories. Fortunately, not the actual source code commit-wise, but they had access to Apache repositories. Cleaning this up was a nightmare, I can assure you. So, as I said, we're at a point where we can finally eradicate cross-site scripting. If you allow your Angular framework to do the sanitization for you, if you have a cross-site scripting vulnerability, it's because Angular has a cross-site scripting vulnerability. And I'm pretty sure that that will be fixed in like half a minute or something. And you update your Angular version, and you're protected again. And that's the really, really important thing here. These frameworks are good at doing this. Let them. Don't work against them. Very important. Deploying a CSP policy gives you the extra edge. It allows you to go even further. And with CSP, it puts you back in control. You can control what is being loaded, what is being executed, where does my stuff come from. And by locking this down, you seriously tie an attacker down. Even if he finds a way in, he won't be able to do anything. He won't be able to execute inline scripts. He won't be able to load code from his own server. He'll have to put it on your server, but that shouldn't be possible, things like that. If you're building an application that's not with a JavaScript framework, follow the coding guidelines imposed by CSP. If you're building a fresh application, you're definitely able to do that. It requires a bit more effort, but really try and deploy your CSP application policy. Use the reporting mode to be warned of potential threats. Keep track of potential reports that may lead to a bug in the application, for example, or in the policy. But also keep track of potential threat vectors. If you see malware popping up on all your users, then you have a serious problem. Somebody is really targeting you. If you see it on one user only, then probably you're fine. If you have 6 applications and one user is vulnerable on all these, or has a problem on all these 6, you may want to warn him, like, dude, something is really wrong with your browser. Please fix your computer. You have the power. Important here, CSP is not a primary cross-site scripting defense. If you only do CSP, you're probably not doing it right. So use it as a second line of defense. First get your XSS defenses up and running. And then finally, CORS. Here we enable the use of cross-origin APIs by design. This security policy has been developed with a lot of consideration for its consequences. Benefit from it by understanding these consequences. I've tried to explain them to you today. I hope I was successful in explaining the consequences of XHR across origins and why it should be restricted. So use the effort that went into developing this policy to essentially do it the designed way instead of using a server-side proxy, for example. Make your API CORS compliant. Maybe somebody wants to use a part of your API that's public anyway, but isn't able because you don't send the right headers. Check this and enable this. And if you have an API that's only for your application, make sure you lock it down by not sending the CORS headers that are supposed to be there on the response. Important side note, CORS does not replace server-side authorization. CORS only prevents a malicious attacker or an attacker from making a request in the user's name to your API. It does not prevent him to make a request he sends himself, not containing the user's cookies, for example. So don't mistake this for server-side authorization. And this finally leads me to the core point and brings me back to what I started with. I started with the fact that the users aren't always to blame, and most of the times users aren't doing anything wrong. Users become the victim of crappy security practices. Users become the victim of a data breach. Users become the victim of malware in advertisements. And for the first time in the history of the web, since a year or two, we actually have the tools to enhance our security. We still have traditional browser security. We still have the same origin policy. It's still at the core of the web. But these server-driven client-side policies are the future. And we have CSP, we have many more. One of the newer is sub-resource integrity that's being developed and being pushed into browsers. And that allows you to check the checksum of files on a CDN. So you can specify, I only want to load this file with this checksum, and if I get anything else, I don't want it. I don't want to load it, I don't want to run it, nothing. And these give you the power to decide what's really important. Especially the security policies for HTTPS, they offer you the possibility to prevent attacks where you couldn't do anything against before, and they are really important. If you're interested in that, come talk to me. I'm here. Use my knowledge, drain it from me. You're welcome to do so. So take advantage of them to build secure applications. And in a closing note, I want to mention that I'm also giving a training course on progressive web security. This is from within the university that we're pushing this towards companies. It starts next week here in Brussels because it's co-hosted by Impulse Brussels. We're already running one since September at our lab in Heverlee, where we have about 14 to 15 participants. It's consultants, people from banks, things like that. And we cover essentially 4 topics in 4 hands-on training days. So we start with HTTPS, we move on to authentication and authorization, we talk about cross-site scripting, and we talk about new browser communication mechanisms such as WebSockets and WebRTC and how they affect your application. If you're interested in this, you can talk to me. You can go to the link here, and maybe I want to see some of you there next week. I've put my slides online as well. I haven't included the link in my slides, but you can find it. If you follow me on Twitter, for example, I'll tweet a link after the session. But I also have a link to my webpage on there, and you can find it there if you want to use them for further references. Thank you for your attention. If you have any questions, I'll be here at least for half an hour or so you can come ask your questions in person to me. Thank you.